Hello, my good friends. Welcome back. Today, let's talk about solving systems of linear equations using elimination. And elimination may be the best method yet. We did graphing and then we did substitution, but elimination is really effective. So let me share my screen with you. Get something to write with because you want to have a record of your thoughts. And let's begin. So let's see here. First thing we need to do is we need to remember what a standard form of a linear equation is. Standard form of a linear equation is going to be ax plus by equals c, where the x comes first, the y term comes second, then there's an equal, and then there's a c. Elimination is a method that utilizes the standard form. So here, activity number 1, demonstration. I'm going to show you how to do it. Solve the system of equations by elimination. So the first thing I'm going to do is check and make sure that each of these equations is written in standard form. I'll call this equation number 1, and it is already written in standard form. So I will, no it's not, no wait. I got to interchange these two things. So 3x goes to the left plus 4y equals 22. There we go. Okay. Now the second one over here, equation number 2. I need to subtract 4y from both sides. So minus 4y, this cancels. So now I got 3x minus 4y is equal to 14. This is equation number 2. Now that they're both in standard form, what I'm going to do is I'm going to stack them on top of each other. Remember in 3rd or 4th grade or sometime, maybe even 2nd grade, when you were learning to add or maybe even multiply multi-digit numbers, you would have to line up the place values, right? Remember when you would do that? Do the same thing here, except instead of place values, we're lining up the x group and then the y group and then the constant column. And in a sense, those are actually place values, if you think about it. Anyway, so equation number 1, I'm going to rewrite down the middle. 3x plus 4y equals 22. And then equation number 2, I'm going to write underneath it. 3x minus 4y is equal to 14. Okay, so what I've got here is I've got the x's lined up on one column here, and then I've got the y's lined up on this column, and then there's an equal sign, and then there's the constants over there on that side. Now, when we did substitution, that method allowed us to get rid of one of the variables by replacing it with its equivalent replacement in terms of the other variable. This one is going to do the same thing here, but it's going to do it rather efficiently. So what I'm going to do now is I'm going to draw a horizontal line, and it's okay, even though it's not a fraction bar, and I'm now going to add these two equations to each other. So I'm going to add this column up. What is 3x plus 3x? Well, that would be a 6x. Good. Now add up this. What is positive 4y minus 4y? Wow. 0y equals, what's 22 plus 14? That would be a 36. You know what? Since I'm going to get 0 y's, I really don't even bother to need that, right? Just erase that off because this cancels. That's the whole point. You're eliminating one of the variable terms. In this case, the y's are being eliminated. What have I got left? Well, I've got 6x is equal to 36. Maybe the spacing there bothers you. Just move it over a little bit. 6x is equal to 36. How do you solve that now for x? Well, divide by 6, divide by 6. I get, whoops, almost done. I get x is equal to 6. But I'm not finished yet. I need to figure out what the y value is. So I have to go back into one of the earlier equations and substitute 6 in for x and solve for y. I will do this one over here on the left. The reason why is because the y is already positive. So come back over here, do a little more math work. So it's going to be 3x, but I know what x is now. X is 6. 3 times 6 plus 4y is equal to 22. Now I solve it for y. So this is 18 plus 4y is equal to 22. Minus 18 here, minus 18 there, cancellations. 4y is equal to, what's that? 4 looks to me like, if I divide both sides by 4, divide by 4, y is equal to 1. Now I can take both of these things and put them together into my final answer. My final answer, the single point that solves both of them simultaneously, 6 for x, 1 for y. There we go. But just as a check, that was on the left-hand side equation. What about equation number 2 over there on the right-hand side? Just for fun, not because you have to, because you should be finished now at this point. Let me go back up here and let me now try it. 6 and 1. So I'm going to come over here and I'm going to zoom in and I'm going to come across here and I'm going to say, oh, it's time for something. So I'm going to say 3 times the x. What was the x again? 6? Yeah, 3 times 6. Is that equal to, I don't know, I'm asking, 4 times the y value, which is 1 plus 14. What's 3 times 6? That's going to be 18. Is 18 equal to 4 plus 14? I got so excited. Look, I'm messing up. Yes, it is. Nice. That's supposed to be a smiley face there. Oh my gosh. That's terrible. Yeah, so the strategy for elimination would be to write the equations first in standard form and then stack them on top of each other in such a way that when you add up the columns, one of the variables is eliminated. Now, this one was ridiculously easy because it was already set up right there to cancel with the positive 4y's and the negative 4y's. How do you do it then if it isn't so easy? Well, remember that the rule of equations is whatever you do to one side of the equation, you have to do to the entire other side. So you can multiply equations, both sides by the same thing, and it's still the same equivalent equation. So let's talk about this one here, activity 2. Solve the system using elimination. They're already in standard form. It's already in ax plus by equals c form, but they don't have the same coefficients. Nothing really is going to cancel there if I combine them. What I want is I want values to have the same number, but I want them to have opposite sign, like we did before, plus 4, minus 4. Same number, but opposite sign. The x's don't have the same number, nor do they have opposite signs, and neither do the y's. So what I need to do now is I need to multiply the top equation or the bottom equation or both so that I get the same constant or I get the same coefficient. So if I'm going to have the same number, I need to be thinking about maybe for the x's 5 and 2. What's the least common multiple of 5 and 2? 10. If I could somehow get one to be 10x and the other one to be negative 10x, that would work. But I think the y's are a little bit easier. For the y's, I don't have to multiply both equations. I just have to multiply one because 3 will multiply into 6 if I multiply it by 2. But I don't just want the same number. I want the opposite sign so that they will cancel when I combine them. So what if I do this? What if I take equation number 2, and which, by the way, I'll go ahead and give them names. This is equation 1, and this is equation number 2. What if I multiply the entire equation 2 by negative 2? What do I get? I'm going to work down, so I'm going to do a little squiggly line here because I'm not adding. If I had drawn a straight line across, it would have been like I've been combining them. So squiggly line, that's just my format. Make sure that you keep it straight. I'm just going to recopy down equation number 1. 5x plus 6y equals negative 8. But now I'm going to copy down the modified equation number 2. Distribute that negative 2 into there. So that's going to be negative 4x, now negative 6y, and if you'll notice now, these are set up to cancel when I combine them, so I'm doing good. Keep going, is equal to, don't forget negative 2 times negative 5, positive 10. That's probably the biggest mistake in doing this, is students forget to multiply the constant stuff over there on the right-hand side by the same number. Okay, now what can I do? Now I'm going to draw my horizontal line and I'm going to add these pieces together. So now coming down the column, what is a 5x minus 4x? That's just a plain old x. And notice that these cancel, okay? What do I get right there? What's a negative 8 plus 10? 2. Believe it or not, there's my x right there. X is equal to 2. Maybe it's too far apart for your comfort. All right, x is equal to 2. Good. Not done yet, because I need to find the y value. Now, how do you find the y value? You can take the x is equal to 2, and you can plug it into the first equation. You could plug it into the second equation. You could even plug it into the modified second equation. Any of those will work. Why is that? Side note, the first rule of thought, the first rule of logic, if you want to call it that, is that whatever something is, it is. What that means is this. If x is equal to 2, it's time for something else. If x is equal to 2 down here, x was equal to 2 right there. And it was also equal to 2 right there. And it was also equal to 2 right there. Every place previously where x was, it's 2. If it's 2, it was 2 every place else. So whatever something is, it is always and everywhere. Okay? So, but it doesn't really matter. I will come up and I will use the first equation. So I'm going to come up here and I'm going to say then now 5 times the x. What's the x? 2 plus 6y is equal to negative 8. And that's going to be 10 plus 6y is equal to negative 8, and then minus 10, and then minus 10, and so this cancels. 6y is equal to negative 18, and so if you divide by 6, y should be equal to negative 3. Put the pieces together now to give my final answer. The ordered pair finally is 2, negative 3, and you've got to give it as an ordered pair with parentheses. Okay. Sometimes you might actually have to multiply both equations to get a value that will cancel. So if you're able to, you can try that one. What do you want to do there? You want to get the x's to cancel, or do you want to get the y's to cancel? If I multiply the bottom one by negative 3, it would give me a negative 9, and it will cancel with the positive 9 there. That would work. Okay. Or if you multiply the top by a negative 2, it would give you a negative 2y here, which would cancel with that one right there. Either way is fine. You can try it both ways and convince yourself of that. Okay. I'm going to move on though. Where's the next one? Here we go. Solve the system using elimination. Okay. Here's equation number 1. Here's equation number 2. What do I want to cancel? If it's in standard form, if not, you've got to rearrange the pieces. Well, the 4 doesn't multiply evenly into 6, and the 2 doesn't multiply evenly into 3. So I don't see an advantage one way or the other. Let me cancel the y's because it'll make the numbers a little bit smaller. What is the least common multiple of 2 and 3? That would be 6. If I could somehow get the coefficients on the y's to be 6, one of them positive and one of them negative, then I would get the y's to cancel, okay? So I'm going to need to multiply both of these equations. So I'm going to multiply the top equation by positive 3, and I'll multiply the bottom equation by negative 2, and that should work itself out. Now, I'm gonna do this one sideways, just to show you an alternate method of organization, okay? So if I distribute 3 in there, this becomes 18x plus 6y equals 6. That's equation number 1. Now equation number 2 becomes negative 8x minus 6y is equal to negative 16. Okay, now it should be set up, this is equation number 2, should be set up to add. So 18x minus 8x, the first column, right here, that's going to be 10x. The y's cancel. Positive 6 minus 6, that's 0. Equals, oh look at this, negative 10. So if I divide both sides by 10, I get x is equal to negative 1. There we go. Now come back over, I'll come back over here to do some work. I'll use equation number 2. Equation number 2 was 4 times the x, but the x I know now is negative 1, plus 3y is equal to 8, and so then it's going to be negative 4 plus 3y is equal to 8. Add 4, 3y is equal to 12, and so y then is equal to 4. Put my pieces together, negative 1 and 4. Nice. Okay, sometimes you got to multiply both of them and include a negative sign. Now, let me talk about two different possible options, and you'll see this sometime later. What if you do your work, and I'm just going to make something up here. What if you said something like 3x minus 5y is equal to 12, and then you get something like negative 3x plus 5y is equal to, negative 6. And when you add those, not just one, but both of your variables drop out and you get 0. 0 is equal to, what is this over here? I don't know, what, positive 6? Both of your variables drop out and you have a true or a false statement remaining. This is false. Okay? What's your solution? No solution. This is the kind of graph where you're going to have two lines that are parallel to each other and they're never going to cross. When both of your variables drop out and a false statement remains, they're parallel lines. They never intersect. No solution for that. But you could also have this. What if I had 3x plus 5y is equal to negative 10, and then negative 3x minus 5y is equal to positive 10, and then when you add them all up, you get 0 is equal to 0. Everything drops out. Like, is that a true statement or a false statement? That's true. And so this then would be an infinite number of solutions. That's when you have two lines that are basically the same thing. And if you think about it there, my equation 1 and equation number 2 are the same line. Okay, there's an infinite number of solutions. All right, so solving then using elimination, you're going to put the equations in standard form. You're then going to multiply, if need be, one or both equations by something so that you will have the same number but opposite sign on one of the variables, and then when you combine them, that variable is eliminated. Okay? It's kind of technical. It avoids fractions. You don't have to do any fractions until the end. Sometimes you can even like multiply stuff around to make them easier to work with in the beginning. So like if you had fraction coefficients to begin with, you could multiply through by a number and clear the fractions. Or if you had decimals, you could multiply through by a multiple of 10 to clear all the decimals, to give yourself whole numbers, as it were, or integers in order to work with. But in any case, may your day be merry and bright, and may all your mathematics be right.